Let us finish our discussion of section 1.3. Last time we discussed inequalities. Please take a look at example 17. We want to prove that 3 to nth power is greater or plus any integer n greater or equal to 0. Here's how we do it. Step 1. For n is equal to 0, this is true. Because if n is equal to 0, left-hand side is 3 to 0 power, which is 1. The right-hand side is 2 times 0 plus 1, which is 1. 1 is equal to 1, so the inequality is true. Step 2. Suppose this is true for some integer n is equal to k, where k is greater or equal to 0. Suppose this. Step 3. We want to prove that this is true for n is equal to k plus 1. We want to prove this. Once again, in order to come up with this, we replace n here and here by k plus 1. Done. We start with the left-hand side. It's over here. Note that 3 to k plus 1 can be rewritten as 3 times 3 to k's power. In order to jump from here to here, we go back to step 2. If we multiply the left-hand side and the right-hand side by 3, the left-hand side becomes 3 to k's power times 3. The right-hand side becomes 2k plus 1 times 3. It's exactly what we have here. So, by step 2, the left-hand side, which is over here, is greater or equal to 3 times 2k plus 1. But what we need is this. We want to prove that 3 to k plus 1 is greater or equal to this. Therefore, what is left is to prove that 3 times 2k plus 1 is greater or equal to 2 times k plus 1 plus 1. We copy this over here. We expand parentheses. 2k times 3 is 6k. 1 times 3 is 3. We expand parentheses here. 2k, it's over here, plus 2 times 1, 2. And then plus 1. Note that if we subtract 3 from the left-hand side and from the right-hand side, this will be gone. Then, if we subtract 2k from the left-hand side and from the right-hand side, on the right-hand side, 2k minus k will get 0. On the left-hand side, 6k minus 2k, 4k. Since k is greater or equal to 0, 4k is greater or equal to 0. Now, question mark is gone. Lastly, this implies this, which implies this. And we are completely done. Folks, any questions here?
In step 2, since we already proved that it's true for n equals 0, could we have said k is greater than or equal to 1?
No, we can't. Please take a look at this word, for some. If you replace 0 by 1, you will not be able to suppose that this is true for some integer n is equal to k, where k is greater or equal to 1, because the only information that we have is the following. This is true for n is equal to 0. Since the only information that we have is that this is true for n is equal to 0, we cannot really suppose that this is true for n is equal to k, which is greater or equal to 1. We just don't know if this is true for, say, 1. Does this make sense?
Yes, absolutely.
Example 18. Prove that 2n plus 2 is greater or equal to 2n plus 6 for any integer n greater or equal to 1. For n is equal to 1, this is true, because if we replace n by 1 here, the left-hand side becomes 2 cubed, which is 8. If we replace n by 1 here, the right-hand side becomes 2 times 1 plus 6, which is 8 again. So, for n is equal to 1, this is true. Step 2, suppose this is true for some n is equal to k, where k is greater or equal to 1. That is this. So, once again, we just replace n by k here and here. Done. Step 3, we want to prove that this is true for n is equal to k plus 1. If we replace n by k plus 1 here, the left-hand side becomes 2k plus 1 plus 2, means 2k plus 3. If we replace n by k plus 1 here, the right-hand side becomes this. We put question mark, we want to prove that this is greater or equal to this. Here's how we do it. We start with the left-hand side. Done. Note that 2k plus 3 is identically equal to 2 times 2k plus 2. Now let us use step 2. If we multiply the left-hand side and the right-hand side here by 2, the left-hand side becomes this, the right-hand side becomes this. So 2 times 2k plus 2 is greater or equal to 2 times 2k plus 6 by step 2. So by step 2, 2k plus 3 is greater or equal to this. But we need to prove that 2k plus 3 is greater or equal to this. So here we put question mark. What is left is to prove that this expression is greater or equal to this expression. We copy it here. We expand parentheses on the left. We expand parentheses on the right. Then, if we subtract 2k from the left and from the right, we'll get 2k here. Then, if we subtract 8 from the left and from the right, 2 plus 6 disappears on the right. 12 minus 8 is 4. Since k is greater or equal to 1, 2k plus 4 is greater or equal to 0. Question mark is gone. And this implies this, which implies this. We are done. Now let us discuss two pretty difficult examples. Please take a look at example 19. The way we ask this question is fundamentally different from any of the previous examples. In all previous examples, question is, prove that ta 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 is true for any integer n greater or equal to 1, or just any integer n, and so on. Here, there is nothing like this. We ask a totally different question. Which number is bigger? So, how to use induction? It turns out that we still can use induction. But in order to use induction, we have to modify this question. Here's how we can do it. Let us show that n to n plus 1 is greater than n plus 1 to n for any integer n greater or equal to 3. In particular, if n is 1000, the left-hand side becomes this, the right-hand side becomes this. Conclusion: if we prove this for any integer n greater or equal to 3, we will be able to come up with the following conclusion: this is greater than this. So how do we prove this inequality? Step 1 is pretty straightforward. We show that this is true for n is equal to 3. If n is equal to 3, the left-hand side is 3 to 4th power, which is 81. If n is equal to 3, the right-hand side is 4 cubed, which is 64. Since 81 is greater than 64, we are done. Step 2, suppose this is true for some integer n is equal to k, where k is greater or equal to 3, because here we have 3. That is, suppose that k to k plus 1 is greater than k plus 1 to kth power. Step 3, we want to prove that this is true for n is equal to k plus 1. If we replace n by k plus 1, the left-hand side becomes k plus 1 to k plus 2. The right-hand side becomes k plus 2 to k plus 1. Folks, any questions before we continue?
Maybe you already answered this, but my computer cut. But why did we choose 3?
Yes, very good question. Folks, let us go back to previous examples. So, please take a look at this. Here we put n is equal to k, which is greater or equal to 1. Why 1? Because in step 1, we showed that this is true for n is equal to 1. And the reason we show that this is true for n is equal to 1 is the original statement. In other words, here 1, therefore here 1. Here 1, therefore here 1. To the contrast, please compare with, for example, this. Since here we want to prove that this is true for n greater or equal to 2, in step 1, we show that this is true for n is equal to 2, not 1. Therefore, in step 2, we suppose that this is true for n is equal to k, which is greater or equal to 2. Now, let us go back to our example. Over here, we want to show that this is true for any integer n greater or equal to 3. Therefore, here 3 and here 3. Now, you may also ask me a question, why do we put here 3? Can we put here, for example, 2? No, we can't, because if you replace n by 2 over here, the left-hand side becomes 2 cubed, which is 8. The right-hand side becomes 3 square, which is 9. 8 is not greater than 9. Did I answer your question?
Yeah, so we started with 3 because that's the first number that we know would work.
Yes.
If you ever receive, or if you ever get a question where you have to figure out what the lowest possible solution would be, is the only way to figure out is just to try, like keep testing and trying and seeing if it fails?
I would say this is one way to do it. Yes.
Okay, thank you.
Okay. But then How do we prove this? Now the question is significantly more complicated. Here is why. Note that in all previous examples, it was easy to extract step 2, a left-hand side term, from step 3, a left-hand side term. For example, 2k plus 3, which is the left-hand side part, is equal to 2 times 2k plus 2, which is the left-hand side part from step 2. Over here, it is not immediately clear how to do it, because we erase k plus 1, 2k plus 2 here, but over here, k, 2k plus 1. How to extract this term from here? So if we try to copy this approach and write, say, k plus 1 to k plus 2 as k plus 1 times k plus 1 to k plus 1, it is not enough. It is not enough to have the same power. We have to have k. But here we have k plus 1. The reason why we were able to jump from here to here easily is the following. When we replace k by k plus 1, 2 does not change. Over here, once we jump from k to k plus 1, both this changes and this changes. So what do we do? Here's one way to do it. First, rewrite k plus 1 as k plus 1 divided by k multiplied by k. Note that after the cancellation, the whole expression in parentheses indeed becomes k plus 1. Next step. If we erase this to the power k plus 2 by algebra, we can rewrite the whole thing as k to this power, which is over here, times k plus 1 over k to this power, which is over here. Next step is very similar to what we did before. Let us rewrite k to k plus 2 as k to k plus 1 times k. Now, if we multiply the left-hand side and the right-hand side here by k times this, the left-hand side becomes this, the right-hand side becomes this. Here is what we do next. Let us collect like terms. Note that over here we have k plus 1 to k's power times k plus 1 to k plus 2. So in both cases we have k plus 1. Note that k plus 1 to k's power times k plus 1 to k plus 2 is k plus 1 to k plus k plus 2. But k plus k plus 2 is 2k plus 2. Similarly, k to first power times k to negative k minus 2 is k to negative k, which is here, minus 1, because 1 minus 2 is negative 1. Do you all see how we jump from here to here? Do you want me to repeat?
Yes, can you repeat it?
So let me start with k plus 1. Do you understand how we come up with this term?
The second term is let's
The
continue.
second term.
Yeah.
So why in the world we have this? Think about this k as about k to first power. Next, please take a look at this k. This k is in the denominator. We divide by k. Since we divide by k, division by k is equivalent to multiplication by k to negative 1. So we can think about this fraction as about the following: k plus 1 times k to negative 1. And now let us expand parentheses. K to negative 1 to the power k plus 2 is same as k to the power negative k minus 2. And now let us put pieces together. Here k to 1, over here k to negative k minus 2, 1 plus negative k minus 2 is negative k minus 1. Is this clear?
Yes, gotcha. Thank you.
So, by step 2, the left-hand side, which is over here, is greater than this. But what we need is this. So what is left is to prove that this expression is greater than this expression. How do we prove it? Let us copy it here. Next, on the left-hand side, we have k to negative k minus 1. If we multiply both sides here by k to k plus 1, this disappears. And on the right-hand side, we get k to k plus 1. In addition, if we factor out 2 here, we get 2 times k plus 1. In order to jump from here to here, raise the left-hand side and the right-hand side to the power 1 divided by k plus 1. If we raise the left-hand side to the power 1 divided by k plus 1, since 2 times k plus 1 multiplied by 1 over k plus 1 is equal to 2, the left-hand side becomes k plus 1 squared. Similarly, if we raise the right-hand side to the power 1 over k plus 1, this will disappear because k plus 1 times 1 over k plus 1 is 1, and this will disappear. This is how we come up with the right-hand side. Any questions? How we jump from here to here?
If you could repeat that again, if you could.
So here's what we do. Let us raise both sides, not to second power, not to third power. Let us raise both sides to the following power: 1 divided by k plus 1. If we raise both sides to the power 1 divided by k plus 1, after we expand parentheses, the new power here will be 2 times k plus 1 times 1 over k plus 1. This will be the power on the left-hand side. Do you understand this?
Yes, I just misheard you. Thank you.
So 2 times k plus 1 times 1 over k plus 1 is 2. This is how we come up with 2. Similarly here, if we raise the right-hand side to the power 1 over k plus 1 will be gone here and gone here. We get this. The rest is easy. Expand parentheses here, done. Expand parentheses here, done. Note that since this is identically equal to this, and in addition, on the left-hand side, we have plus 1, obviously, left-hand side is greater than right-hand side. Lastly, this implies this, which implies this, which implies this, and we are completely done. Folks, any questions?
I have a question. At the beginning, we assumed that the left-hand side was bigger than the right-hand side.
Yes.
Why did we assume that if it doesn't say in the original question, which is bigger? Did we just guess?
That's the whole point. This is why this exercise is exceptionally difficult. You have to guess. You have to modify the original question first in order to answer the question. Looking at this, you do not think about math induction at all because there's no n. Did I answer the question?
Yes, thank you.
Okay, guys. But now, please take a look at this. Here it's written solution version 1. It turns out that we can prove this inequality using mathematical induction significantly easier if we modify this inequality first. Please take a look at version 2. So here is same inequality. Let us copy it here. Next, let us divide the left-hand side and the right-hand side by n to nth power. Since n to n plus 1 can be rewritten as n to nth power times n to nth power can be cancelled. After we cancel out n to nth power here and here, the left-hand side becomes n. Now, please take a look at the right-hand side. If we put parentheses around the whole thing, we rewrite the right-hand side as n plus 1 over n to nth power. Lastly, let us split this fraction into two pieces. N divided by n is 1 plus 1 over n. So let us rewrite this as this. It's exactly what we have here. And now it turns out that it is significantly easier to prove this by math induction than this. Here's why. As before, in step 1, we show that this is true for n is equal to 3. Now, step 1 is a little bit more complicated. If we replace n by 3 here and here, we got this. 1 plus 1/3 is 4/3. We cube, done. Now, either by calculator or if you move 27 to the right, we come up with the following conclusion. 64 divided by 27 is lesser than 3. We are done with step 1. Step 2, suppose this is true for some integer n is equal to k, which is greater or equal to 3. That is this. Now let us prove this for n is equal to k plus 1. Let us prove this. Oh, excuse me. Yes, we should switch the sign. it turns out that it is much easier to deduce this from this than this from this. Here is why. Let us start from the left-hand side. It's over here. It's easy to see that this is equal to 1 plus 1 over k plus 1 to k's power times 1 plus 1 over k plus 1. Next, since k plus 1 is greater than k, 1 over k plus 1 is lesser than 1 over k. Therefore, the whole thing on the left is lesser than the whole expression on the right. And now observe that what we see over here is the left-hand side from step 2. So, if we multiply the left-hand side here and the right-hand side here by this expression, this inequality becomes this. Means, by step 2, the left-hand side is lesser than the right-hand side. Now let us expand parentheses. K times 1 is k. K times 1 over k plus 1 is k over k plus 1. Lastly, since k plus 1 is greater than k, k over k plus 1 is lesser than 1. We are done. This is lesser than k plus 1. It's exactly what we need. Folks, any questions here?
I have a question.
Yes.
So in step 1, we say like the smallest case is 3, right?
Yes.
So kind of like what the other person was asking earlier about the smallest case. So since we're not really proving that like the 1 plus 1 over n to the n is smaller than n, we're just really trying to get to like which of the two numbers is smaller. Does it really matter that we figure out which one's the smallest case? Can't we just like pick a number that's smaller than 1,000 and 1,001 and then use that as our smallest case?
Oh, yes. So you can use here any number which is greater or equal to 3. Absolutely. Problem is, how would you do step 1? If, for example, instead of 3, you have 100, how would you show that this is true for n is equal to 100?
Well, maybe not 100. That probably like say like 6 or like 5 or something like that. Like and
Well,
like on the test, if I'm not like wasting time to try to find out the smallest integer, can't I just use like 5 or something like that?
or basically your question is, do we have to put here smallest integer? No.
Yes. Okay.
No, you don't have to put here smallest integer.
Okay.
I put here 3 because even if you put here, say, 6, it is not so easy to do computations. You have to raise 6 to 7th power. But once again, in order to solve this problem, you do not have to put here the smallest possible integer. Did I answer the question?
Yes, thank you.
By the way, you can take a look at this remark at home. One can show that even a stronger inequality is true. Over here, we prove that 1 plus 1 over n to nth power is lesser than n, but even a stronger inequality is true. 1 plus 1 over n to nth power is lesser than actually 3. But it is significantly harder to prove this than this. Last example. We already discussed this inequality. And I said that we cannot use mathematical induction to prove this inequality directly because the right-hand side does not depend on n. However, if we first come up with an auxiliary inequality that implies this, that can be proven by induction, then the problem will be solved. Here is an auxiliary inequality. It's over here. Note that since 1 minus 1 over n is lesser than 1, this implies this. And now let us use math induction to prove this inequality. Let us show that this inequality is true for any integer n greater or equal to 2. Step 1. For n is equal to 2, this is true. Because if n is equal to 2, the left-hand side becomes 1 over 2 squared. The right-hand side becomes 1 minus 1 over 2. Obviously, 1 over 4 is lesser than 1/2. Step 2. Suppose this is true for some integer n is equal to k, where k is greater or equal to 2. Suppose this. Let us prove this for n is equal to k plus 1. We want to prove this. So we start with the left-hand side. It's over here. By step 2, this sum is lesser than 1 minus 1 over k. It's over here. We add the last term. Done. So by step 2, this is lesser than this. But what we need is the following. We want to prove that this is lesser than this. Therefore, here's what is left. We want to show question mark that this term is lesser than this term. Copy it here. Done. Subtract 1 from the left-hand side and from the right-hand side. 1 is gone. Next step. Let us multiply the left-hand side and the right-hand side by the following expression. K times k plus 1 squared. Done. Now we cancel out k here. Done. We cancel out k plus 1 square here. Done. We cancel out k plus 1 here. Done. Expand parentheses. Expand parentheses. And now, if we add k squared to both sides, negative k squared will be gone. If we combine together negative 2k and k, the left-hand side becomes negative k minus 1. The right-hand side, after we cancel this term, is negative k. Obviously, negative k minus 1 is lesser than negative k. Question mark is gone. Finally, this implies this, which implies this, and so on, which implies this. Problem is solved.